All right, so now we are gonna go and do our lab. Kidney regulation of osmolarity. Actually, so yeah, before we actually go and actually see what, let's discuss our hypotheses. Yeah. And some of you did a good job on the hypotheses. Some of you did not turn them in. You really do need to keep up on this stuff. And like, again, what we're going to talk about now isn't going to make as much sense if you haven't actually been thinking about it in advance either. So we have these 4 groups. It's supposed to be caffeine. So again, what is our independent variable here?
Water, salt, and caffeine.
Yeah, so, or I should more completely be like intake, the amount of intake of water. Again, this person has water, no salt or caffeine. This person has certain amount of water, a certain amount of salt. So we have different amounts of intake we're putting into the body, certain amounts of water and or salt and or caffeine. And what are our dependent variables?
Volume of urine,
exactly,
salt concentration, and a specific gravity of the urine.
So these different qualities of the urine, the amount you're making, how much salt, and specific gravity. And then for each of these groups, I asked you to come up with a hypothesis, about how volume and salt concentration and specific gravity we're going to compare between them and why. So let's start with group 1. This is kind of the most straightforward because it's just water, a large amount. Again, 800 mils of water is like one of these big gulps of soda or something. It's a lot of water. So what would you expect to find looking at the volume, sodium chloride concentration, and specific gravity of the urine in somebody who has just drank 800 mils of water, and now you're going to wait and see what happens?
I think they'll have the second highest volume after caffeine, because caffeine's a diuretic and there's not taking any salt, so there's not going to be any reclamation of water.
Yeah, so but you're going to expect to lose, you're going to have to let go of a lot of water to maintain the balance. And especially if you compare this one here, you're taking in the same amount of water, but you're also taking out salt. We're taking in salt. So you're going to have to be, you're probably not going to let go of the water quite as quickly as you would in this case, because your osmolarity is a little higher. That's going to probably make you want to hold on to a little more water to keep your body at the right concentration. Whereas in this case, because we're having the caffeine, assuming, did anybody actually look up caffeine and try to see if there's any evidence of it being a diuretic?
I couldn't find anything.
Right.
No,
So,
it says it's diuretic, but I couldn't find evidence either.
Well, what I found out is it prevents sodium absorption. That's all I found out.
right. So, I mean, one of the places, where could you look if you were trying to decide whether or not, whether caffeine really seems to be with actual evidence a diuretic or not?
PubMed.
PubMed, exactly. That's the whole, hopefully you're starting to get a feel like that's a place to go to figure out, is this real or not? You know, if you go there, you'll find that it's a little unclear. If it is the reality is, even if it is a diuretic, it's kind of a mild one. It doesn't do that much. I found more convincing data that it increases intrarectal pressure, that it definitely makes you poop after you drink coffee, but it's not as likely to make you pee. You know, I think a lot of times people drink a bunch of coffee and then they gotta pee, but it's because they just drank a whole bunch of liquid, not necessarily because the caffeine is doing it. But again, we'll see from the data and see what we can see. So we'd expect a high amount of volume compared, especially to this group who've not taken in any water at all. Probably a little more than this group where you actually have a higher overall osmolarity because of bringing the salt in, maybe a little less than this one if we think of caffeine as a diuretic. What about sodium chloride concentration?
There wouldn't be any.
It will be low in group 1.
Probably be low, you know, compared to the other groups. You know, the more salt you're taking in, the more salt you probably need to let go of. And the other thing I would say, concentration is solute over solution. So if you have a large volume, you are again, if I have the same amount of salt in a large volume or a small volume, I can have the exact same amount of salt, but have a much higher concentration here, right? So the larger volume you have, you know, probably the less concentrated things are going to be, just because whatever you've got is in a larger volume. Which is actually going to be important. We're going to look at, like when we come over here to group 3, you know, how much volume do we expect in the person who only drank a tiny little shot glass of water?
A small amount of volume or none.
Yeah, it'd be a very small volume compared to the other groups.
High concentration of salt.
And we're going to expect, so we're going to be getting rid of salt. And the high concentration, though, is going to be a mix, though, of both amount of salt, but the fact that whatever salt is being released is actually in a very, very tiny volume, right? So we're going to look, when we're comparing the results here, we're going to look both at the concentration of the salt, but we'll also look at actual total weight of salt that's being excreted out of the body, which we can do. We could just, if we multiply, right, if we take like concentration, like mils of, or I should do grams, like grams of sodium chloride per liter would be a concentration, you know, times liters of urine. Like what was the volume that you actually peed out? then I'm going to end up getting how many grams did you actually pee out in that particular voiding. So we'll look at both of those. We'll look at both the concentration, which is the thing we're measuring, but then we can actually calculate the actual amount of salt in the pee, because all you need to do is take the concentration, multiply times the volume, and you've got the actual grams of salt. What about group 2? What would you expect to see in group 2? Oh, I'll actually get back. What about specific gravity?
The highest amount of specific gravity
Wait, which one?
for group 3.
So group 3, if we have, in general, we're going to probably find that specific gravity mirrors the sodium chloride concentration. Again, specific gravity is the amount of dissolved stuff, basically. It's, officially, it's the measure of density of your urine compared to the density of water. So if your density of your urine is almost like just water, specific gravity will be 1. If the density is higher, then the specific gravity will be greater than 1. And I mentioned the values tend to go like very salty urine is like more like 1040 or something. It looks like a little number, but that's considered a big number in specific gravity. I should mention the way we're going to measure specific gravity is a little different than the dipstick. We saw how to use a dipstick last time. In this lab, we use something called a urinometer. So we basically have a little vial and we have the urine in it. So, and then we have a little float. Does anybody here ever make beer or wine or anything? Use a little hydrometer? Like one of the ways to tell like how much sugar is in your stuff that you're going to ferment, and if the fermentation is done, is you have this float that will floats up higher if there is more density, it drops down lower if it's less dense. It's just Archimedes' principle. So there's going to be a little float that we put in the urine. And it's got little gradations on it. And you can actually just read, depending on how high this is floating, there is an actual value. It'll just say, what is the specific gravity right on the little float. And if your urine is more watery, then the float will be lower. If the urine is really concentrated, maybe I'll draw it. In fact, let's make it really concentrated. More concentrated urine is often much darker as well. So when I have my urine that's really concentrated, the float tends to go up pretty high. And that's where the value is, where so this would be like a very high specific gravity. This would be a low specific gravity. So depending on how high or low the float is going to depend on the density of the urine. And then that's going to define where that line is, or where the surface of the urine is on the little readout. So you'll see this in the little picture or in the video. La, 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 la. So we have these groups. Group 2, what do we expect in group 2?
Also a high volume like group 1 of urine because they took in a bunch of water.
Right, so you'd
But-
expect them to lose water, and again, and also to keep water balance. In this case, though, they're also going to have to be losing some salt for salt balance. I mentioned last time, I'll mention again, this amount of salt is not that much. I've lowered it over the years so people don't feel uncomfortable. Some of the values we used to use earlier on when I first started the lab, people would just feel really uncomfortable. And I figured it's better to like not have people feel bad than not have as dramatic results. So this amount of salt will make a bit of a difference, but it's not going to be as dramatic as if you were eating like 5 grams of salt. But there is this thing, if you're taking in salt as well as the water, you're probably not going to let go of the water quite as readily, right? Because here you're getting really low osmolarity because wherever you're at, we're just diluting it straight up. Here we're diluting you, but we're also adding in solute as well. So where the osmolarity is not going to drop quite as much. So we would expect our response is not going to be quite as dramatic in terms of releasing water to recover from that. So are there questions about all these different groups? Does anybody have any questions, comments, or anything around what you'd expect or why? All right, so let's.
Actually, yes. So like what's happening with group 4?
So with group 4, it's going to depend on what caffeine really does. So I would say this one, you can have different hypotheses that might or might not be supported or might be partially supported. If caffeine is truly a diuretic, what would we expect?
Large volume of urine.
Or in fact, larger volume of urine than group 1. So the same amount of water,
Yeah.
but adding something that increases urine output under the same conditions, we would expect the largest volume out of here. And likely, low concentration and low specific gravity if you're having a large volume, no matter, even if you secreted the same amount of solute, if you have a larger volume, you are going to have a lower concentration.
Mm-hmm. Okay.
And, by, then it'd also be a lower specific gravity. Or we might find caffeine does, Jamba was saying that he was reading that caffeine inhibits sodium reabsorption, which means that would actually mean we could have a larger volume because we are not keeping the salt in the body, so we're not keeping as much water in the body, but that would also mean we'd have a higher sodium concentration if we're letting go of more sodium. So that would be another hypothesis. Or another hypothesis would be that it's not a diuretic at all, in which case group 4 and group 1 would be very similar. Maybe, maybe if you're peeing out the caffeine metabolites, maybe that would increase specific gravity a bit. So there's lots of different possibilities, which we won't know until we look at the data.
Okay.
All right. So what you're going to see now, so normally what you would do is you would void your bladder to start, just pee out every last drop, take whatever you are supposed to take. Drink your water, eat your salt, take your caffeine. That's like time equals 0. And then start a timer. And every half hour, you're going to measure those 3 dependent variables. Again, it's actually kind of fun because you get to go and everybody's walking up and down the hallways with big beakers of their urine and stuff. And we're not going
One question, Professor, sorry to interrupt you. And the sources of variability?
Oh, that's a good point. So what are sources of variability in this lab?
What you ate or drank before lab?
Absolutely. Right. So we are going to throw out the first voiding because, who knows what you were eating or drinking before. But, it has happened where we've had the person who drank 800 mils of water, barely peed at all over the next 2 hours, and I've had to have a talk with them of like, you really should stay more hydrated. This is not good, right? So if somebody is just really dehydrated and they drink 800 mils of water, it might not result in a lot of water loss to keep a water balance if they're super dehydrated to start with. Right, so that is a huge source of variability. What people have been eating and drinking ahead of time. What are other sources of variability?
Medications?
Medications, they can affect your urination pretty dramatically. And actually non-pharmaceutical things, like most people drink coffee, so if you've been drinking coffee already, like and if coffee is a factor in this, we're not controlling, like, have you had caffeine ahead of time? And some of the people who aren't taking the caffeine tablets probably have caffeine on board because they drink coffee or they drink a Red Bull or whatever. That's another huge source of variability. What are other ones?
Kidney issues.
Yeah, you could have any things that is kind of messing with your kind of kidney function. That would, hopefully people would be able, if they knew they had something like that going on, you would take yourself out of the data pool.
How about a body size? Like if you are really fat or big, then you would be able to like tolerate much more water in your body and keep it.
That probably does make sense. Yeah, because if you're have overall larger body, you've got like a larger volume of blood, and the same amount of water you take in is probably not going to affect your osmolarity in the same way as if you were more compact. So yeah, there's lots of things like that. Speaking, I never mentioned this, but it's kind of interesting. Or maybe I did. Like people who are taller versus shorter. If you think about what their heart is doing, to pump the blood against gravity all the way up to your brain every day, constantly for your entire life, this person is more likely to have their heart give out earlier by the end than this person. There's more stress on your cardiovascular system if you're much taller, which I always thought, yes, it's kind of interesting. So, but anyway, that's more on the side. Let's share screen again. Share screen. Let's do this. So you are going to watch me take a it's my P, and I'm going to analyze it and show you what you would have done for each of your collections. And this is so you have kind of a more of a realistic sense. You're going to be looking at the data in the spreadsheet, but I want you to at least see, how did this data get recorded? All right, so I've been in group 3, which was just drinking 80 mils of water and taking 1.5 grams of salt. And this is a half hour since I did my initial voiding of my bladder and taking my treatment. And here's the amount of urine that I've got. Again, I'm collecting it every last drop, because I care about the volume. So this is not a clean catch like you were doing in the urinalysis lab. You're going to collect from the beginning to the end of the flow. And first thing I want to do is figure out the volume. And you should notice, this is a really big beaker. It's a liter beaker. For group 3, it doesn't have to be that big. You're not going to pee out that much. But some of these other groups have a lot of urine coming out during this thing. So you really do need a big beaker for this experiment. So you could catch like, a half a liter of pee and not have it overflow, because we do want every last drop. And I can look here, roughly, it's less than 100. So when I think about which one of the cylinders makes sense, I'm going to probably take the one that's 100. This is going to get lost if I put it in one of these bigger ones here. So I'm going to pour it in. And I can go, and I can see it's about 31, 2, 3, 4, 5, 36 mils. And that is the first part. I'm also going to want to measure its specific gravity. The specific gravity, I'm going to use this urinometer. It's basically a little vial and this float. It's kind of a hydrometer, like if you were making beer. It's the same idea. And depending on the density of the urine, this little float will float further up or sink further down, and the level of the urine on this little scale here is going to tell us the specific gravity. So typically you add about maybe 2/3 of the height here of the tube. If you did not pee at all, you're not going to be able to get a value. And again, if you didn't get enough urine to actually float the float, you would just have no reading for specific gravity. It wouldn't be 0. 0 is not a valid. It would just be null. You don't have a value. But I have enough urine. I'm going to now put my float in. Make sure it's not going to overflow. It looks good. You want to give it a little spin. I'm going to put it down here. Just kind of little style. You give it a little spin as you drop it so it doesn't stick to the walls. And then as it settles in, I can look here and it's about turn it a little. So about 0.028 is my, or 1.028 is my specific gravity for this. I'm going to mark that down. Then the last part of this is I'm going to get the sodium chloride content of my urine. For that, I am going to need a little test tube and a dropper here. And so basically I'm going to need 10 drops of my urine. And so this is described in the lab manual, but it's basically a quantitative test using color change of this chemical reaction, which I'm going to describe right here. It matters that the drops are actual, like, well calibrated drops. This is a quantitative test, and it depends on numbers of drops that you're adding of different reagents. So it matters that I'm careful to add exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops of my urine. Then I'm going to add exactly 1 drop of this potassium chromate solution. And now I'm going to add silver nitrate solution drop by drop by drop. And this forms a precipitate. And you'll see as a drop hits into the solution, it's going to turn brown for a moment, but then will probably become yellow again. And I'll keep adding drops of silver nitrate until this solution here stays brown. And the total number of drops that I add here are going to be the value of the total milliliters per, or milligrams per milliliter of sodium chloride that I have in there. Again, you can see it's yellow when I start. Does this help?
Yes.
Okay, I'm going to add in a drop. Do you see little brown show up? And add 2, 3, 4, 5, 6. I need to kind of look at it. Still looking 7, 8. Oop. Not still, it's not staying brown. 9, 10. Not quite yet. 11, 12. Ooh, it's almost there. 13. I'd probably give it one more. 14. That's brown. So 14. It took 14 drops. So that would mean I've got about 14 grams of sodium chloride per liter, or 14 milligrams of sodium chloride per liter in my urine, which probably makes sense given that I'm probably pretty dehydrated being in group 3. Okay. All right, so that gives you a sense of how we actually measure the variables. And here under this kidney lab data here, this is the actual data that you're going to use for your discussion. So in your discussion, you are going to look at this and you'll have to talk about whether this data supports your hypotheses or not, and kind of what happened, what do you notice? So let us take a look here. Let's view. I'm gonna make it smaller. Wait a second. View. All right, so this is showing, again, time equals 0, we don't care, right? Whatever the values were at time equals 0, that's going to depend on what you've been eating and drinking before we started the experiment. That's why I have this kind of blocked out. We don't really care. It's not interesting. 30 minutes, 60 minutes, 90 minutes, 120 minutes, those are the response to whatever you ate and drank at time equals 0. So this is going to be interesting. Again, we have the data for group 1, group 2, group 3, group 4. Again, there's one thing I should mention. Let me kind of view. If you take a look here, there's quite a few of these squares for specific gravity where there is not anything. I don't know if can you see that? Like all of these squares here don't have anything for specific gravity. That is because this is group 3. If you take a look at the volumes are really small. They're like 14 milliliters, 0 milliliters. They didn't pee at all. You have to try to pee at every half hour. Even if you don't feel like you have to pee, you try. Usually you can, right? You don't usually feel like you have to pee until you've got like a couple of 100 mils in your bladder. But if you only have like 11 mils of urine, that's not enough to actually float the float. Actually, it's not, it's worth just mentioning briefly here. So let's say I only have this much urine, and the float is just sitting on the bottom there, it can't float. So I can't use this method to get my specific gravity. This is not zero. Right? Sometimes people say, oh, I didn't get a value, so I'm going to write zero. Right? Zero is a number. Right? Zero means you measured something and the value was zero. Zero in terms of specific gravity would be bizarre. It would mean like a vacuum or something. So when you do not actually have data, then you usually do like this, like kind of null. This means there is no value, as opposed to zero, which is a value zero. Like, how many eggs do you have in the fridge? If you say zero, that means you checked and there are no eggs in the fridge. If you just don't know, like I've never looked in the fridge and the fridge is locked, I can't tell you how many eggs are in the fridge, then it would be this. There is no value to that question. I don't have a value for you. So in the data, when you see those blank things, particularly in group 3 for specific gravity, it's because, you can measure volume. If you try to measure the volume and they didn't pee at all, I can say, well, they didn't pee at all, so the volume is zero. I measured how much pee and there was zero pee. So the volume can be zero, but the specific gravity is not going to be zero. The specific gravity is just going to be, we can't measure it. So does that make sense? All right. Go back. Oh, it's locked. I will unlock it in a few moments. That's weird. What? Okay, here we go. So let us take a look at the results. So volumes. And we can, let's do like maybe 125. So here we see after 30 minutes, 60 minutes, by 60 minutes, an hour after they have taken in their different treatment, we can see a pretty dramatic difference between groups 1, 2, and 3, and between 1, 2, and 4, and between group 3. The group that did not have much water and ate the salt is peeing out very little. The other groups are all peeing out an appreciably large volume. So this totally makes sense. Well, let me, I go to annotate. So if you look here, now we can compare. So we say group 1, 2, and 4 are all similar in that they're all kind of going up pretty dramatically, but then we can look for subtle differences. Group 1 and group 4 only differ by caffeine. And we can say they're pretty similar, although if you want, you can say the caffeine group looks like slightly larger volumes over time. Not dramatic, but a little bit. So we do see a difference, but it's not much. I would say, in my mind, it's hard to know whether these are different because of a real reason or they're different just because they're always going to be a little different if you get a bunch of people and let them pee in a thing. Group 2, on the other hand, while we do have a large volume compared to like group 3, it is appreciably lower than the groups that did not take salt. So here we do, I think, see evidence that if you drink the water, but also drink salt, because your osmolarity is not gonna go down as much, you're not diluting your overall concentration as much, your body is not gonna respond with as dramatic a release of water. So the volume, I mean, when I look at this, these make sense to me. And when you're writing up your discussion, again, you want to discuss things kind of in this larger kind of point of view, like I'm talking about, just thinking about osmolarity and volume and water balance. Don't get too concerned about what's going on in which tubule or something. Think about it more on this kind of functional level of what is the kidney doing and why do these results make sense. If we look at sodium chloride, let's take a look at that. Let's see. Whoops, I gotta. There it is. I'm going to clear the drawings. Sodium chloride concentration. Oh, we don't. Again, this, in the big picture, this is not shocking at all, right? Group 3, the group that didn't drink much water and ate the salt, has much higher sodium chloride concentrations than any of the other groups. All of the other groups are pretty low, although if we do look, group 2, the one that ate the salt tablets, does have a little bit higher salt concentration compared to the other groups, which you would expect. And like I said, the amount of salt we had the subjects take was actually not that dramatic. The original protocol I adapted this from, I'd have people vomiting. And then I lowered it and they weren't vomiting as much, but they were still like cramping and feeling really crappy and stuff. So I kept lowering it until, people didn't complain about discomfort, but then we didn't have as dramatic results in the output. So, but again, this is not surprising results. This kind of makes sense. What I think is kind of surprising is this. So like I mentioned, concentration very high here, but concentration is solute, grams of the solute, grams of the salt divided by the liters, the overall volume. So part of why this concentration is really high is this volume is really low, right? If the denominator is getting really small, then this thing is going to be getting bigger. So the next graph that I have for you is looking at the concentration times the volume. So that's going to just basically give you the actual grams of salt that were peed out. So I'm calling it NaCl amount. And if you look here, like how much salt was actually getting peed out for each pee, you can see actually in group 3, they actually had the least amount of salt leaving their body. But I think that was because they had very little like actual urine to dissolve it in, right? So one of the reasons why you always have to have some volume, even if you're trying to conserve water, you're going to have a very small volume of very concentrated urine, is you need at least some urine to dissolve the stuff in to get it out of your body, right? So if you don't have some liquid to dissolve the stuff in, then you're not going to be able to pee it out. So this idea of, this is, you're getting rid of as much salt as you can, but since you have so little volume, it's hard to get rid of as much as you'd like. If we look at group 2 compared to group 1, again, group 1 is blue, group 2 is fuchsia. We actually see in general, the group that ate the salt tablets was actually peeing out more salt, than the group that just had pure water. So we actually do see the body getting rid of salt here. If we're looking at the actual grams of salt leaving the body, group 1 is holding on to, is not losing that much salt, whereas group 2 actually is losing more salt. And consistent with Jamba's statement about caffeine inhibiting salt reabsorption, we are seeing actually the group that had more caffeine does seem to be losing more salt than the group that just had pure water. So that's kind of interesting as well. And then finally, specific gravity is not going to be that interesting. It's basically mimicking the salt concentration. So group 1 with group 3 with the really high salt concentration has a really high specific gravity. Groups 2, 3, and 4 with the low salt concentration have a lower specific gravity. Group 2, which had a smaller volume, with a reasonable amount of salt, have kind of a, slightly higher than the other two. Groups 4, even though group 4, we said actually has quite a bit of salt because it has a lot of volume as well. That means that it's going to keep the overall concentration down, right? Because concentration, like I said, is a function of both the amount of salt, but then also the total volume. So are there any questions about this data? The data actually makes sense. Like if you think about what the kidneys are doing, you're thinking about water balance, salt balance. It does, these results are consistent, and it does give you some sense, like at least with this data set, caffeine might make you pee a little more, but it's not dramatic.